We can use Euler's method to approximate a solution to a differential equation or find a point on the solution curve. So to find an approximation for yi, we start off at yi minus 1 and we add delta x multiplied by the slope of the tangent to the curve at yi minus 1, which is the derivative. And that'll give us delta y. And therefore our approximation to yi is yi minus 1 plus delta y. And as we mentioned, delta y is equal to delta x by the slope of the tangent to the curve at xi minus 1. So you can see that the larger delta x is, the worse our approximation is. So this is the exact value, and this is our approximate value. So you're going to get a larger error as delta x becomes larger. So what we do is use smaller divisions to approximate yi while starting at yi minus 1 and taking several steps in between. And we'll see that in a coming example problem. Let's use Euler's method to approximate y of 0.4 using this differential equation where the initial condition is given and the step size is given. So let's try Euler's equations. And the initial conditions. So x0 is 0, delta x is 0.1, y0 is 0.2, and therefore the initial slope is equal to minus y0 by this differential equation. And now we can start our steps. So when I equals 1, x1 is equal to x0 plus delta x according to this equation. So that's 0 plus 0.1, which is 0.1. And y1 is y0 plus delta x by y dash 0. So that will be 0.2 plus 0.1 by minus 0.2, which is 0.18. And therefore the derivative, y dash 1, is equal to minus y1 according to this differential equation. So that will be minus 0.18. And now you can set I equals 2 and then calculate x2 and y2 and y dash 2 using these previous values and keep stepping through until x is equal to 0.4. So you can calculate y of 0.4 and post your answer in the comments.